least squared regression line. So, the least squared regression line, also sometimes known as the line of best fit, is going to be the line that best runs approximately through the center of our data. So here we have the same example that we had in the last PowerPoint, the last video of percent in poverty and percent high school graduation rate. And we want to choose which of these do you think would be the line of best fit. And it's a little bit hard to see here because you have to kind of ignore the other lines when you're focusing on one line. But we'll do our best here. So we want to see which of these best fits the linear relationship between these two variables. It's definitely not C, right? C has a slope of 0, and we know that this line should have a negative slope. So that's not going to go through all of our data. This green line, B, seems to be well under most of the data. It's going to underestimate most of the points. So not that one. Between A and D, they both kind of go through the middle, but the yellow line, D, seems to overestimate things up here and underestimate things down here. So A is going to be our best answer choice. All right, it goes approximately through the data. At all points on the line, it's got about as many points above the line as below the line. Residuals are the leftovers from the model. So the data point is the fit, the predicted point based on the model, plus the residual. Or more often, what we're going to do is say that the residual is the actual minus the predicted. All I did was rearrange that to solve for the residual. It's going to be the actual minus the predicted. So if your actual point is higher than your predicted point, you get a positive residual. And if your actual point is lower than your predicted point, you get a negative residual. So the difference between the observed value and the predicted value. Observed minus predicted. So remember, these were each of these data points is a state, or DC. So this is Rhode Island. The actual value for this percent, this is probably 81% high school graduation, and they've got about 10% in poverty. According to our line, that for this high school graduation, they were predicted to have about 14% in poverty. So they're much lower. They have negative residual of negative 4.16. Whereas DC is up here, right? For their percent high school graduation of about 86%, they are predicted to have about 12% in poverty. And actually, they've got about 17%. So they have a positive residual of 5.44. So how do we get a line of best fit? We want a line that has the smallest residuals. And we want the smallest residuals on average. Not just, all negative residuals or something like that. We want the large residuals and the smaller residuals to kind of balance each other out. So we could minimize the sum of the magnitudes of the residuals, but that's tricky and not the best method. Instead, we use the sum of the squared residuals, and we want to minimize that because we want this the line that best fits all of that data. So that has the smallest residuals, or the smallest sum of squared residuals. This is most commonly used. It's easiest to compute by hand and using software. And just like with some other things, like our standard deviation calculation and our chi-squared calculation, it amplifies the magnitude of the larger residuals. So something, the much larger residuals have a much larger effect on the LSRL. And we want that, right? A residual that's twice as large is usually more than twice as bad. And so we want something that takes that into account. So this gives us the least squared regression line, the LSRL. And this is in the form y hat equals alpha plus beta x. Y hat is your predicted y value. Alpha is your intercept, the y-intercept of your line. Beta is the slope of your line. And x is your explanatory variable. So for the intercept, the parameter is alpha. That's the intercept for the population LSRL. Usually we don't have, usually we can't do the entire population, so we would be taking a sample, and the point estimate for that intercept would be A. The parameter would be beta, but when we take a sample, our point estimate is going to be B. All right, so here is our scatter plot again. We know the mean and the standard deviation of the y's and the x's. We can find the slope of the regression. So the slope of the regression line, B equals SY over SX times R, right? R is our correlation coefficient. And so you would need to figure these out using a calculator or a computer. But B is SY, the standard deviation of the Y's, over the standard deviation of the X's times R. This should be on your AP formula sheet. So in this case, we can find the slope of the regression line, the standard deviation of the y's divided by the standard deviation of the x's times our r of negative 0.75 will give us a slope of negative 0.62. When it asks you to interpret the slope in context, because that is something that they very frequently ask, this is how you do it. For each additional unit of the explanatory variable, we would expect the response variable to be higher or lower on average by slope. Or we could say our model predicts that the response variable will be higher and lower. Same thing. Right? So for the example that we just did with the high school graduation rate and the percent in poverty, we would say for each additional percentage point in high school graduation rate, so that's the unit in the explanatory variable, we would expect, or our model predicts, that the percent living in poverty, our response variable, will be lower because it's negative, because our slope is negative, on average by slope 0.62 percentage points. The intercept is where the regression line intersects the y-axis. The calculation of the intercept uses the fact that the regression line always passes through x bar, y bar. So this is just a fact about the regression line, right? X bar, y bar would be the mean of the x's and the mean of the y's. It's not necessarily one of your actual points. It's just some point that is the mean of the x's and the mean of the y's. And the regression line will always pass through that point. And so once you've calculated the slope, if you do, y bar equals a plus bx bar, you can solve for a if you know b and x bar and y bar. You can plug all of those in and solve for a, and that will give you the intercept. So, with our percent high school graduation rate, if we plug all of this in, we get an intercept that's like 65-ish. What's it going to tell? 64.68. If we plug in the x bar and the y bar. So they also could ask you to interpret the intercept in context, which when your x variable or your explanatory variable is 0, the response variable is predicted to be whatever your intercept is. So when the percent high school graduation rate is 0, the percent living in poverty is predicted to be 64.68%. Now, is this a reasonable value? Probably not. Right? Where are we ever going to find someplace that has a 0% high school graduation rate? Very unlikely in the United States. All of our data are here between 70 and 100%. So using a line that is meant to fit these data to predict something this far away will not be accurate. And that's often going to be the case with the intercept. The intercept on its own is not a particularly useful point. It is not going to tell us anything because we would not realistically expect to see a value of 0 in the explanatory variable. And you may end up getting like a negative. If you have a positive LSRL, you may get a negative value for your intercept. And it may not make sense in real life to have a negative value for that response variable. But so that point on its own may not be useful, and that's okay. What it does is that it just ensures the placement of the LSRL for the data that we have, and allows us to then predict values of the response variable based on some hypothetical explanatory variable for values of the explanatory variable that are similar to the values that we actually have. So may not be useful on its own, may not make sense on its own, but it makes sure that the line does fit the data for the range that we actually have data for. So, all right, which as long as the correct interpretation of the intercept, the intercept is not a point increase or point decrease. It should be something about states where the high school graduation rate is 0, or there are no high school graduation rates. So, it's a D. States with no high school graduates are expected, on average, to have 64.68% of residents living below the poverty line. Right? In places where the explanatory variable is 0, the response variable is expected to be 64.68%. It is not C because that indicates causation. That high school graduate having no high school graduates causes 64.68% of residents to live below the poverty line. we don't know that that's true. Remember that from way back in Unit 1, we can't infer causation based on an observational study. We would have to do an experiment to determine causation, and it is both impractical and unethical to randomly assign people to graduate high school and determine poverty on a large scale. Right? So here, right, we said the intercept in this case is not very useful. It's not reliable. We would not necessarily expect that this trend is going to continue for very small percentages of high school graduation. We cannot be sure that the trend continues for values of the explanatory variable that are well outside the data that we have collected. So, we would say that this is extrapolation. We'll talk more about extrapolation in a minute. So this gives us the regression line. The predicted percent in poverty is 64.68, which was our intercept, minus 0.62, which is our slope, times the percent high school graduation. So from this regression line, we can calculate a predicted percent in poverty for any high school graduation rate. Just plug it right in. Right? So again, this is our interpretation of the slope and the intercept. The slope for each additional unit in your explanatory variable, the response variable is expected to increase or decrease on average by the slope. And then the intercept, when your explanatory variable is 0, your response variable is expected to equal whatever the intercept is. Note, again, these statements are not causal. They're not saying that the x value causes the y value, unless this is a randomized controlled experiment. We are just making statements of correlation, not statements of causation. Using the linear model to predict the value of the response variable for a given value of the explanatory variable is called prediction. And it just involves plugging in the value of x into the linear model equation. There is going to be some uncertainty involved with the predicted value. The strength of the fit of a linear model is most commonly evaluated using R squared. You have this formula, the square of the correlation, but it's most commonly the square of the correlation coefficient, right? It's literally your R value squared. And this would be how you would find that R value squared by hand, but you're not ever going to have to do that by hand. It's awful. That's what we have calculators for. So, what is the point of the R squared value, which is called the coefficient of determination? And so the coefficient of determination tells us what percent of the variability in the response variable is explained by the model. And then that means that the remainder of the variability is explained by variables not included in the model or by inherent randomness in the data. So for the model we've been working with, right, our R value was negative 0.62. So our R squared, you square negative 0.62, and it's 0.38. So your R value is always between negative 1 and 1, which means that your R squared is always between 0 and 1. A negative R indicates a negative correlation. A positive R indicates a positive correlation. R squared is not going to indicate the direction of the correlation. R and R squared have no units. They're just numbers. and an R of 0 is no linear correlation. So, the correct interpretation of R equals negative 0.62, R squared is 0.38. 38% of the variability in the percent of high school graduates is explained by the model. 38% of the 38% of the variability in the Y value in the response variable, the percent in poverty, is explained by the model, or explained by the percent of high school graduation. So, R squared percent of the variability in the response variable is explained by the linear relationship with the explanatory variable, or is explained by the model. Same thing. So, told you we were going to come back to extrapolation. Applying a model estimate to values outside the realm of the original data is called extrapolation. Sometimes the intercept might be an extrapolation, such as this case, right? The intercept is well outside the range of where our actual data fall. So this would be an extrapolation. So, examples of extrapolation. Women may outsprint men by 21:56. Women sprinters may be outrunning men in the 21:56 Olympics if they continue to close the gap at the rate they are doing, according to scientists. That part that I underlined is important because that is a big assumption that is not necessarily supported. Right? So here they've got the data of the times, the winning Olympic 100-meter sprint times for men and women. And you can see that the women's times are decreasing decreasing faster than the men's times. The slope of the LSRL for the women is steeper than the slope of the LSRL for the men. But they have extrapolated that to say that in 21:56, 135 years from now, that the women will outsprint the men. And this is an extrapolation because that is so far beyond what we actually have data for. This requires the assumption that the men and the women's times will continue changing at this same rate for the next 135 years, and that may not be true. That would be a very large thing to assume. This is my favorite. So, as you can see, by late next month, you'll have over 4 dozen husbands. Better get a bulk rate on wedding cake. Because yesterday she had 0 husbands. Today she had 1 husband. If she continues on at this same rate, next month she'll have over 4 dozen. So, what conditions need to be met for the least squares regression line? Linearity. We need to have an approximately linear relationship between our explanatory and response variables. We need nearly normal residuals. The residuals should form an approximately normal distribution. We need constant variability. Excuse me. We need constant variability. So, linearity. The relationship between the explanatory and response variable should be linear. There are ways to fit a model to nonlinear data, but we are not going to be dealing with that in this class. That is something that you will look at if you take more statistics classes in college. So to determine whether your data are linear, you can use a scatter plot or a residual plot. So the residual plot takes the x value as the x value of the data, but then your y value is your residual. So here you have positive residuals in the middle and you have negative residuals on the end, and so that's represented in the residual plot. So these data are not linear because you get this curved shape in the residual plot. These data are linear because they appear to be randomly distributed about the LSRL. You have some positive and some negative residuals everywhere on the line. Same thing here. The correlation here is weaker in the third one, but it still appears to be approximately linear because you don't see any type of pattern in the residual plot. You just get randomness in the residual plot. So even though the correlation is weaker, we would still say that this is linear data. All right, so looking at these points again, right, we looked at Rhode Island, where the percent of high school graduation is 81%, the percent in poverty is 10.3%. When we use our LSRL to predict that, we got a predicted value of 14.46. So that gives us a residual of negative 4.16. So here in the residual plot, that's here, where the x value is 81 and the y value is negative 4.16. And then DC was this point, high school graduation of 86%, percent in poverty is 16.8. The predicted value down here was 11.36, so that has a positive residual of 5.44. So this point is here on the residual plot. It's still at the x value of 86, and then the y value is the residual of 5.44. Nearly normal residuals. This may not be satisfied when there are unusual observations that don't follow the trend of the rest of the data. So you can use a histogram or a normal probability plot for the residuals. So here is a histogram. If you just calculate all of the residuals and then do a histogram of them, you would get something that is approximately normal. The normal probability plot plots the theoretical quantities against the sample quantities. So where based on how many standard deviations away from the mean and how they should be distributed, and you should end up with about a straight line. We don't really do the normal probability plot in here. Don't worry about it. And then condition 3 is constant variability. So the variability of points around the least squared line should be roughly constant. So the variability of residuals around the 0 line should be roughly constant as well. When we look at the residual plot, we should see, again, randomness. When we see the residuals increase as x increases in a kind of fan-shaped or Christmas tree-shaped pattern, that's called heteroscedasticity, and that's bad. Not bad. You want to check the residual plot. You can check the residual plot or the scatter plot. So, this doesn't actually show what heteroscedasticity looks like. Heteroscedasticity, if I have, this is my LSRL, and I've got points that are like this, and then as my x values get bigger, they get farther away from the LSRL, that would be heteroscedasticity, and that's bad. We don't like that. On the residual plot, it would look the same, except they're going to be increasing in variability around the x-axis. That's heteroscedasticity. That violates the constant variability condition. Which condition is this linear model most obviously violating? It's not linear. It has a clear curved pattern, which you can also see in the residual plot. Which condition is this linear model obviously violating? It's the constant variability. So this is the heteroscedasticity, where you can see it better in the residual plot, where it start out close to the line and then get farther and farther away. So that's the fan shape or the Christmas tree shape. So sometimes the AP test will ask you to interpret computer output. You get something that looks like this, and it wants you to determine the LSRL from this. And the good news is that this is giving you the LSRL, you just have to know which points are which. So this is the regression output for predicting the heart rate in grams of cats from their body weight in kilograms. And this is based on a data set of 144 domestic cats. So this, where it says intercept, that is your y-intercept. And so everything on that line is associated with the y-intercept. This would be the estimate for the y-intercept, meaning that is your A in your regression line. You don't really need to worry about the standard error, the t-value, and the p-value for the intercept. The variable, the explanatory variable, when it's listed here, this is going to be your slope. And it'll usually be listed as the name of the explanatory variable. This is because when you do a multiple regression, you have multiple explanatory variables and you have to differentiate between them. We're not doing multiple regressions in this class. That's for higher level college stats. This sometimes also, the intercept will sometimes say coefficient. That's also the intercept. But your slope is usually going to be labeled with the explanatory variable. The estimate, so this is the estimate of your slope, that's your B. The standard error, the t-value, and the p-value are used for confidence intervals or hypothesis testing on the slope, which we'll talk about later. And then it also will give you your R value, your R squared value. So I think this is the S. This is supposed to be over here. But this is the standard deviation of the residuals. That's what that is, the standard deviation of the residuals. This is your R value, or R squared value. Don't worry about the adjusted R squared. You don't need that for right now. So if we were trying to find the LSRL for this, the LSRL R, right, is y hat equals A plus BX. Our Y value, we are predicting the heart rate of cats. So heart weight with the hat, because it's predicted, is A, which is negative 0.357, plus the slope, B, is 4.034 times the body weight is your explanatory variable. And that's how you interpret the computer output. It's literally just you pick the numbers out of here and you put them into the formula. Piece of cake.